So when I zoom into class, I still get more absent.
Pardon?
When I zoom into class online, I still get more absent. Is there like a limit to how many times we can zoom in?
So, I mean, are you enrolled in the class?
Yeah.
Well, then, so you have to be present in class 70% of the time.
Mm.
So, whatever number, 70% of what, 30 class meetings is like 2021.
Oh, okay.
So, up to 9, I guess,
Okay.
approximately.
So that means like the other 30%, like the Zoom class wouldn't count.
Correct.
Okay.
Right. You have to be in person in class to be counted as present for the purposes of attendance.
Okay. Right. Can there be an exception just for today? Because I do have another obligation I need to get to.
I mean, you don't have to be here today, but like it's not, I'm not gonna, if at the end of the quarter, it's like on the board, we can talk about it. But like as far as we're concerned right now, you should still be fine.
Okay. No, right now it's looking pretty good.
Oh, okay. Well,
Because that was
well,
the first three because I
sure.
really do.
Well, you should make the choices you need to make. Obviously, if you need to be somewhere else, I understand. Just try to come to the future classes.
Okay. Right. Is there a way I could sign in today?
I mean, if you're not going to stay, no.
Yeah, okay.
Go.
Have a good one.
That's it. All right. Where are we at today? Let's turn off the lights here. All the lights, all the lights. Yeah, all the lights. Nice and super freaking dark. Oh my God. Maybe I should hold on a second here. It feels extra dark, doesn't it? Okay, that's better. All right. Still, I feel like I'm working in the middle of the night or something over here. Is there people out there? Okay. Here comes the attendance sheet. What can I say? So as far as I know, you're still talking about solving differential equations in class, unless you did something different today. You start talking about 3D graphing stuff yet? Good. Then we'll just continue talking about solving differential equations because there's a few different things I feel like we should talk about. And some of these get kind of gnarly. So let's go ahead and I was actually trying to find one of these examples here that's kind of gross. And we'll kind of go back and forth between separable and first order linear. Let's actually, yeah, let's. Sorry, I had to restart my computer for reasons and everything went away. Yeah, we'll do okay. We'll do a couple more tank problems and then we will kind of mix it up a little bit. So Co-17C, that's not C, 17B. And today is 11 slash what, 5? Yeah, 5. So again, tank problems. We talked about one at the end of class last time. It's a pretty typical setup. I'm fairly confident that Dell will have you do a couple tank problems. It's usually his style. Probably Burke as well. But look, well, if she's having, well, you still don't have to do that. Okay, sorry. Talking to myself here. So let's look at this example. So we'll do the first tank problem is going to be kind of the easier version of the tank problem. The second one is going to be the harder version where the flow in and the flow out are different volumes. So let's say a tank contains 1,000 liters of brine, meaning salty water, with 15 kilograms of dissolved salt. Sure. Pure water enters the tank at a rate of 10 liters per minute. The well-stirred solution, mixture, whatever you want to call it, drains from the tank at the same rate. So the question we're eventually going to ask is how much salt is in the tank after 20 minutes? But before we get there, we're going to take a couple intermediate steps. In fact, I want you all to do this first step. So the first step I want you to do is to write down the differential equation. I'll help you out a little bit here. So I would point out that we're going to say that I should draw a picture actually first before we get too crazy here. Here's my tank. It's got 1,000 liters of solution in it, starting with 15 kilograms of salt. And then we're going to put in pure water at 10 liters per minute. And we're going to drain out not pure water, or whatever the mixture of the solution is, also at 10 liters per minute. So I want you, and then one more thing, and then we're going to say that S of T is the not the percent typically, but the amount of salt in the tank at time T. So what I want you all to do is to set up the differential equation for this system. So you're going to write the rate of change of salt is equal to whatever the rate going in is minus the rate going out. So give that a whirl. Try to figure out how much salt is going into the tank every minute and how much salt is coming out of the tank every minute. I should. I can really hear you in here. So typically with these problems, the rate in is always pretty easy. In fact, in this problem, it's super easy. The rate that the salt's going into the tank is 0 kilograms per minute. Right? There's no salt going into the tank because we have pure water going in. So our rate in is 0. Our rate out is, so the rate out is going to be the concentration of salt in the tank. That's going to be the amount of salt divided by the volume in the tank. And then multiplied by how fast we're draining the tank, which is in this case is 10 liters per minute. So in this particular example, writing this without all the units, we have that ds dt is equal to negative s over 1,000 times 10, or let's just simplify that and write it as negative s divided by 100. I didn't write s of t because I'm trying to like kind of write it more easily to deal with. And I'll point out here, this is an example where I probably wouldn't use a first order linear differential equation, right? Even though you could, this one is so easy to do separately, we might as well do it as a separation of variables. So we're just going to now, so we set it up. If you really wanted to, you could write, kilograms per minute if you really cared to have some units on there because liters cancel. But then part B, we're going to solve the system. And in this case, we're going to use it with separation of variables. So we've got ds dt equal to negative s over 100. When I'm separating variables, I want to keep as much stuff on the right side as possible, or as little stuff on the left side as possible. So here, I'm going to not bring over the 100. I'm going to keep it on that side. I'm going to say that 1 over s times ds is equal to negative 1 over 100 times dt. You could do other things. That's probably the easiest way to deal with this, though. Then we're going to integrate both sides. And I'm going to try to pretend like I can ignore the absolute value when I take the integral here, and I will. So the integral of 1 over s is going to be the natural log of just s equal to the integral of negative 1 over 100 is negative 1 over 100 times t plus the constant c. Last time we did talk about how the absolute value here eventually just goes away because of the way constants work out. If you have questions about that, come see me in office hours tomorrow or Friday, because I'll remind you, I don't have office hours after class today. So I won't be seeing you after class today. Solving this, we're just going to e both sides. We get e to the natural log of s equals e to the negative t over 100 plus c. We end up rewriting this as just good old s equal to, I would encourage you to get comfortable doing this because it happens a lot. E to the negative t over 100 times e to the c, and then e to the c we call something else. I like to call it capital A. You can call it whatever you like. So S of t is equal to a times e to the negative t over 100. Now we're not done, because in this problem, even though they didn't explicitly say some initial condition, there is an initial condition, which means we should solve for any constants that are in our problem. Our initial condition is the amount of salt in the tank at time 0 is 15 kilograms. So we know that S of 0 should be equal to 15, which is equal to a times e to the negative 0 over 100. But that e to the negative 0 over 100 is just e to the 0. That's just 1. So our a value is 15. So our actual solution is that S of t is equal to 15 e to the negative t over 100. Now we can find, so I'll point out, this question could have been written the way we wrote it, and it could have said after this is, how much salt is in the tank after 20 minutes? But that question requires us to do all of this to be able to answer that question. Because what that question isn't saying is that you have to find salt as a function of time, which means you have to set up and then solve the differential equation. So whenever you see, especially when you ever see this kind of tank problem, there's always the implication that you're going to have to set up and probably solve a differential equation to answer any questions about it. So here, now the question we really wanted to ask was, how much salt is in the tank? After 20 minutes, I would double check and make sure my initial setup was using t measured in time, t measured in minutes. So that, all right, because maybe it was actually t measured in hours, and 20 minutes corresponds to 1/3 of an hour. If I look back at my question, it says we were putting stuff in at a rate of 10 liters per minute. So using 20 minutes is appropriate to plug in here. But it is important because sometimes people like to do tricky things with units being different. So pay attention to the words and the units. So our answer here is going to be just S of 20, which is going to be 15 e to the negative 20 over 100, or simplifying 15 e to the negative 1/5. Whatever that happens to be, I didn't particularly write it down. Something that I think is interesting that I could see either of your instructors asking, but they might not, is the following fact. When you have a tank problem like this and the volume going in is the same as the volume going out, like we're putting in 10 liters per minute, we're taking out 10 liters per minute, what is always going to be true is that the concentration of whatever your thing in the tank is going to get closer and closer and closer and closer and closer to the concentration of the stuff you're putting in. So in this problem, since we're putting in pure water with no salt, eventually we're diluting away all the salt. And if you think about it, if you look at this function here, as you let time go on and on and on and on and on, this value is going to get smaller and smaller and smaller because you're going to get e to the negative infinity. That's going to get closer and closer to 0. So the amount of salt gets closer to 0, which means the concentration of salt in the tank also gets closer to 0. I didn't say this at the end of last class, but last class, the problem we were doing, I don't remember what we were putting exactly, but we were putting in, I think, something that was like, I want to say it was 2 pounds of salt per gallon. And if we had let that process go on and on forever, it would have ended up having the amount of salt in the tank tend towards 200 pounds of salt in this 100-gallon tank, which means the concentration is getting closer and closer to 2 pounds per gallon. That is not a coincidence. That is something that always happens as long as the volume going in and the volume going out are the same. Which kind of makes sense if you think about it, right? If you just kept like adding in the solution that had the same concentration forever and ever and ever, and you kept draining it at the same rate, eventually the thing you're putting in is going to just kind of be like, well, that's the concentration we're getting closer and closer to because, right, we're putting stuff in, taking stuff out. That's kind of how it works. Now, Things are more complicated if the volume going in and the volume going out are not the same. Let's see. I know I have an example here. 1 second. Yeah, actually, yeah. This is similar to the example we did last time. I don't love it that way though. I'm just double checking to see if I really want to make it like that. Sure. Yeah, we'll do it like that. Okay. Let's look at another situation here. So similar situation, another tank problem. Here are the important details. So the tank holds, that's not a good way to say it. Sorry. The tank has 100 gallons of pure water, and we are adding a solution, a salt solution with a concentration of 2 pounds per gallon at a rate of 5, apologies, 5 gallons per minute. Now, here's where things are different. The well-stirred mixture is going to be drained at a slightly slower rate at 4 gallons per minute. So notably, at least this tank for a while better be pretty big because every minute we're going to be increasing the volume by 1 gallon, right? We're adding in 5 gallons every minute. We're taking out 4 gallons every minute. So we're netting 1 gallon every minute. That's why I didn't want to say the tank can hold 100 gallons because it needs to be able to hold more than that if I'm going to be increasing the volume. That's why I had to change that word, but not something we should get hung up on. So here's our picture. Our tank that starts off with no salt in it, but 100 gallons of water, 0 pounds of salt. And we're putting in a concentration of 2 pounds of salt per gallon at a rate of 5 gallons per minute. Sorry, it's a little ugly over there. And we're draining it at a rate of 4 gallons per minute. And again, the first step to this problem is always to set up a differential equation. So set up a differential equation for how much salt, or for, I should say, how the amount of salt is changing. So we're going to say that dsdt, I'll say it again, the amount going in is almost always easy to find. It's usually just your concentration, well, both of them are just your concentration multiplied by your rate. It's just that in the going in instance, they're both constants. So the concentration going in is 2 pounds per gallon. The rate it's flowing in at is 5 gallons per minute. And just like last time, things cancel appropriately. We see that we're putting in 10 pounds of salt every minute, minus how fast we're pulling the salt out. So the concentration going out is especially complicated in this example. So the concentration broadly is the amount of salt divided by the volume of the tank. So the amount of salt, well, that's just our function. It's S of t. It's always S of t or whatever we're calling it. It could be A of t if you like A for amount better than S for salt. So it's S of t, how many pounds of salt there are in the tank at time t, divided by the volume of the tank, which is changing. So the past problems, the volume has just been however much volume the tank held because it was putting in the same amount as taking it out. But now, every minute, the volume is increasing by 1 gallon. So we're starting off with 100 gallons at time 0, and then we're going to add t gallons every minute. So after 1 minute, we're going to have 101 gallons of the tank. After 2, 102, and so on and so on and so on. And then we're still going to multiply that by how fast we're letting it drain at, which is 4 gallons per minute. And I forgot this is pounds and this is gallons. This is 4 gallons per minute. So here's my condensed differential equation without all the units. Again, you don't have to write the units. I just find it helpful to make sure that I'm getting the right thing. These cancel, I get pounds per minute. So that's 10. And these cancel, and I also get, these cancel, I also get pounds per minute. I get 4 times S divided by 100 plus T. And this is not separable. I know you look at it like, oh, maybe, but no, it's not. So if you want to see if you want to try to separate it, here's what you should do. You should get a common denominator. So let's answer the question, or let's affirm the fact that it's not separable. If you tried to separate this, you could say, well, ds dt is equal to, I'm going to multiply 10 by 100 plus t over 100 plus t. I'm going to get 10 times 100 plus t minus 4s, all divided by my common denominator, 100 plus t. And now you might see that there really isn't a way I can bring the s's to the left side without also kind of bringing some t's along with it. So this is not separable. A big no on separable here. And this will always be true if the volume going in is different than the rate the volume is going out. If the volume going in and the volume going out are the same, you can separate it, but I still don't usually recommend separating it. All right, so if it's not separable and you're asked to solve it, there's only one other thing you can do. That's actually a really good thing to know, right? If you're asked to solve a differential equation, it either has to be separable or it has to be first order linear. There's nothing else we're able to do in this class. So let's write it as a first order linear in the typical way. I'll remind you from last time, the general format for a first order linear is something like your derivative plus the function of your input times your function equal to some other function of your input. So we're trying to solve for y, or in this case s. We should be able to write it as the derivative of s plus a function of t times the function s equal to a function of t. So what that really amounts to is just bringing this 4s over 100 plus t stuff over to the other side. So we're going to rewrite our equation ds dt equal to 10 minus 4s over 100 plus t as ds dt plus 4s over 100 plus t equal to 10. And then I'm going to do one more thing. I'm going to do 2 more things, actually. I'm going to rewrite ds dt as s prime, just because it seems more natural in the first order linear context. And then I want to rewrite this as essentially the function without the s in it. So I'm going to write this as plus 4 over 100 plus t times s equal to 10. There is my p of t, and just for continuity, there's my q of t, to write the things on both sides. So look, I've written this in the standard format for a first order linear differential equation. Now we can do all the things. So, did Dr. Diddell talk about how he wants you to solve this in general? He wants you to do all the steps, I assume? Yeah, okay, good. That's what I figured, but it's good to be sure. Okay, so first we're going to find the integrating factor. The reason it's called this is because it's literally the thing that after you multiply both sides of the equation by it, it allows you to complete the integration. That's why we're calling it that. The integrating factor, I like to call it mu, but you can call it I if you want. Mu of t is e to the integral of our p of t dt. So in this case, our mu of t is equal to e to the integral of 4 over 100 plus t. And try to be careful, try to make your plus signs and your t's look different enough so that you can tell which is which. Here, integrating this, we're going to get e to the 4 times the integral of 1 over 100 plus t is the natural log of 100 plus t. And then we bring the 4 up as a power. So that's equal to e to the natural log of 100 plus t to the fourth, which is just 100 plus t to the fourth power. And how much do I want to say here? Yeah, I can't stress enough. It's really important when you do these problems, if your integrating factor simplifies, to simplify it as much as you can. I really don't want to be multiplying both sides by e to the 4 natural log of 100 plus t. It's much nicer to multiply both sides by 100 plus t to the fourth. Because if you don't do this, it's going to make the integration on the right-hand side very, very challenging, if not impossible, without simplifying it. All right, so now, yeah, we have to show all the steps. Okay, so we're going to multiply everything by 100 plus t to the fourth. So check out what we get. We get 100 plus t to the fourth power times s prime plus 100 plus t to the fourth power times 4 over 100 plus t times s equal to 10 times 100 plus t to the fourth. Sorry, I'm running out of room here. And I think it's worthwhile to simplify this here. I'm going to rewrite this as 100 plus t to the fourth times s prime plus one of those 100 plus t's cancels, and you get 4 times 100 plus t cubed times s equal to 10 times 100 plus t to the fourth. Now let's take a look at this for a minute. This right here, this left-hand side, is the derivative of a product. Here's the nice thing about this product. The product that is on this left-hand side is always going to be the product of your function, s or y or whatever you're calling it, and your integrating factor. So you could just say parentheses, boom. I know it has to be s and my integrating factor. I'm not even looking at what's going on up here. Every time. Every time, every time, every time. Except I need a derivative right there. So now you can see, oh yeah, look, it's the derivative of s times the not derivative of the other thing. That's that part right there. Plus the derivative of the other thing, 4 times my stuff to the third power times the derivative of my stuff, which is 1. So right, we should be thinking of the chain rule still. And then you leave the s alone. It's exactly the derivative of that product. Every time we do first order linear differential equations with this process of using the integrating factor, that is always what happens. I know I keep saying it, but I really want to stress that literally every time it's going to happen that way. The other side is just what it is. 10 times 100 plus t to the fourth power. And now we anti-differentiate both sides. The left side, the antiderivative of that derivative is just going to be s times 100 plus t to the fourth power. The right-hand side, we actually have to do the integration. I'm going to pull the 10 out in front and write it as 10 times the integral of 100 plus t to the fourth. And while you could do a u substitution here, I think you can probably get away without doing it. The integral of this should be 100 plus t to the fifth divided by 5, and nothing else since the coefficient of t here is just 1. So this is really going to be 10 times 100 plus t to the fifth power over 5 plus c. And then we solve for s. So we're going to say that s of t is equal to all of that divided by that. So I've got 1 over 100 plus t to the fourth. Sure, let's put that 10 on top. Let's say we have 10 over that times 100 plus t to the fifth, 5 plus c. And it's technically fine to leave it unmultiplied out. I personally prefer to multiply it out. So if we multiply this out, you're going to get, let's see, 10 divided by 5 is 2. So you're going to get 2 times 100 plus t to the 1. And then you're going to get plus 10 times C, which you could just write as another constant if you really wanted to. I probably would. C divided by, sorry, yeah, divided by 100 plus C to the fourth. And that's our final answer. Without having, oh, is there a final answer? No, it's not, right? Because this was a tank problem. I know it's been a minute since we started the problem. It was a tank problem, right? Right, there was some salt and some stuff. Yeah, right. This was a whole tank problem. And the tank started off with how much salt in the tank? Zero. So that should be pretty not terrible to find the actual particular solution for. So now to solve for C, we're just going to say S of 0 is equal to 2 times 100 plus 0 plus C over 100 plus 0 to the fourth. And that should equal 0. Well, cool. We can solve for C. I've got 200 plus C over 100 to the fourth power is equal to 0. So minus 200. C is going to equal negative 200 times 100 to the fourth. That's kind of big. Yeah. Yeah, it's kind of big. Interesting. Which I guess is the same as negative 2 times 100 to the fifth. So then we rewrite our final solution as S of t equal to 2 times 100 plus t plus, I probably should have written minus, negative 2 times 100 to the fifth over 100 plus t to the fourth. And then, finally, after you've actually found the solution, then you can answer any questions about how long it takes until there's so much salt in the tank, or how much salt is in the tank after so many minutes. So we can ask the question like, how much salt is in the tank after 100 minutes? Well, we're just going to plug in 100. So we say that S of 100 is 2 times 100 plus 100 minus 2 times 100 to the fifth over 100 plus 100, which is 200 to the fourth. That's kind of interesting. Feels like we could simplify that kind of somewhat. I'll point out this does simplify kind of nicely in that we have 2 times 200, which is 400, and 100 to the fifth over 200 to the fourth. So if we look at this here, I have 2 times 100 times 100 times 100. I know this is kind of silly, but just bear with me. Now, here's what you really should do. You should use a calculator. But like, if we had to simplify this because someone wanted us to, we have 200 times 200 times 200 times 200. And then look what can happen. This 2 and this 100 can cancel that 200. 100 and 200 leave me a 2. 100 and 200 leave me a 2. 100 and 200 leave me a 2. And I've got 100 divided by 8, which is 50 over 4, which is 25 over 2, which is 12.5. So let's say we've got 400 minus 12.5, which is 387.5 pounds of salt. Be careful. They might ask you, instead of asking this question, they could ask you, what's the concentration of salt in the tank after 100 minutes? So then it would just be whatever we found. So the concentration after 100 minutes would be, well, it'd be S of 100 divided by whatever the volume in the tank was after 100 minutes, which is going to be not 100, right? Because the tank has been getting more voluminous as time is going on. It would actually be this 387.5 divided by, well, after 100 minutes, I think the tank has gotten to be 100 plus 100 gallons, so 200 gallons. And that's going to be some number like 190 something, 193.75 pounds per gallon. That's not right. My decimal is way off. So here's a good time to think about if your answer makes sense, right? I clearly wasn't thinking about that when I wrote this down. If you look back to the beginning, we're putting in a concentration of, I lost it here. I think our concentration was, what was it? I think it was 2 pounds per gallon. Sounds maybe right. Yeah, 2 pounds per gallon. Seems like it'd be real hard to get to a concentration of 193 pounds per gallon. I think my decimal is off a couple spots here. I think it should have been 1.9375 pounds per gallon. And here's something I don't know if it's true or not. So I said something earlier that if the volume going in, the volume going out are the same amount of volume, then your tank's concentration will tend towards the concentration you're putting in as time goes on and on and on and on. That could also be true if the volumes are different. I don't know though. And it's not really super important to know, but I was just noticing it looks like we're getting pretty close to 2 pounds per gallon here. So it could be plausible that it doesn't matter if the volume is the same or not. The concentration still gets closer and closer to whatever the concentration you're putting in is. I'd be curious to know. I'm not sure how you figure that out though. All right, let me take a pause for a second here. So first order linear, definitely need to know how to do. It's very, very important that you make sure before you start anything, first you ask yourself, is it separable or is it first order linear? Sometimes it could be both. You can pick if it's both. I generally think if it's both, unless it's really, really easily separable, the first order linear, although it's hard, the process is a little harder, the algebra is usually a little easier. So if it were up to me, I would recommend first order linear versus separable in most tank problems, unless except for like the first one we did today where you're putting in 0, that's real easy to just do as a separable, but most of the time it's not. The second thing I wanted to say was after you've identified specifically it's first order linear, you must write it in the exact same format. It has to be it has to be just your derivative plus function of your other variable times your function to the first plus equal to some other function of your other variable. If it looks different at all, you have to fix it. I will point out if you have a minus sign here, that's easily fixed by writing plus negative of whatever your function is. Okay, let's look at some other problems. I know there was a couple people asked me about that I felt like were kind of worth mentioning. Let me see if I can find it. Yeah, oh yeah, there was two. There's a couple. So yeah, so let's change gears a bit here. Let's say we want to solve the following differential equation: xy prime is equal to y plus x times e to the y over x. And there's a problem here. It's not anything we know how to do. It's certainly not separable. I can't get y prime with just y's, right? Like usually if you have addition over here, you're kind of trapped. Like sometimes you can fix it, but y plus x e to the y over x, there's no way of breaking the y's apart from the x's. And it's also not first order linear. It is first order. I've only got a first derivative. I don't have a second or a third or a fifth derivative, but it's not linear in the variable y. Sure, I've got y to the first there, but that y up there is really making it not linear at all as far as y is concerned. So it's neither. And this problem has additional instructions I hadn't written down yet, which is we're going to use a change of variable. And the change of variable is letting v equal y divided by x, which I don't see. Well, I see one place. Okay, I see it right here. So I'm starting with xy prime equal to y plus x e to the y over x. And I see that this can certainly turn into v. I really want to get this to a place where I only have two variables essentially, like whatever the function is and its derivative typically, and then like the other variable. So I need to make the rest of this look like y over x somehow. I think it's probably reasonable to divide both sides by x. So I can rewrite this as x times y prime divided by x equal to y divided by x plus x divided by x times e to the v, e to the y over x. I'm still call it that for now. And now it's going to be a lot nicer. These x's cancel, they become 1. These x's cancel, they become 1. And my remaining y over x's both get to become v. And we're almost there. We've got y prime equal to v plus e to the v. But we don't really know what y is as a function of v. We would really like this to look a little bit more typical. Like this is, right, y prime here, just a reminder, y prime isn't dy dv. Y prime we're thinking of as dy dx, right? Up here, when you had just y's and x's, that's what we were thinking. So to deal with y prime, we have to kind of think of what y is equal to and replace it. So I'll note, using v equal to y over x, we can say that v times x is equal to y. And then y prime is going to really be the derivative of v times x. Oh, tricky. Product rule over here. So we're going to get v prime times x plus v times x prime, but the derivative of x is just 1, right? We're differentiating with respect to x. And that's equal to v plus e to the v. And then I can subtract v from both sides and get that x times v prime is equal to e to the v. And now we can separate variables because my v prime here, right, we're thinking of v prime as a function of x, so we can say that v prime is really just our dv dx. So we have x times dv dx equal to e to the v. We divide both sides by e to the v. We bring the d. Oh, there's so much moving around here. We have 1 over e to the v times dv equal to 1 over x times dx. I don't love this problem personally, but it is a problem that comes up occasionally. But it kind of feels like, how would you do this if someone didn't tell you how to do it? I agree. How would you do it if someone didn't tell you? I don't know. I didn't know how to do this problem until I read the instructions. I think there's still, even after reading the instructions, it's still a little bit tricky, right? Knowing that you have to make this look like what you need to make it look like, and then replace the y with the vx here, it's a little bit tricky. Continuing on here, we have the integral of not 1 over e to the v, but e to the negative v is equal to the integral of 1 over x. I think I'll stop there for that one because I do want to cover one other thing. So I'll point out the rest of this problem is to integrate both sides, solve for v, and then once you solve for v, you have to remember that v is equal to y divided by x. So you're going to do some work. You're going to get v equal to some function of x. And then after you do that, then you're going to say, but really, v is equal to y divided by x. So you get y divided by x equal to some function of x, and then you get y equal to x times that function of x. So your v is equal to y is going to be x times that. A little bit tricky. Well, there's one other one here that also is kind of wonky that I wanted to address. Yeah. Which is the following problem. Maybe. So unfortunately, I think it's unfortunate. Some of these problems have a whole lot of just constants for your, or like letter constants as opposed to like actual numbers, which is just a pain, right? It's fine, but it can be challenging sometimes. So here's a problem that we should look at for a second. The spread of an infectious disease, such as influenza, is often modeled using the following autonomous differential equation. So we have di dt is equal to beta times I times n minus I minus mu times I. So I is the number of infected people. N is the total size of the population. And beta is a constant. It's what is it? It's a constant determining the rate of transmission, but we just really care it's a constant. And mu is also a constant. And it's the rate at which people recover. So this one, we just want to find all the equilibria. The reason we're doing this problem, and we're probably gonna run out of time. So this problem is related to another problem that we're going to talk about, I guess, on Friday, where you then have to actually kind of solve it, and solving is kind of a pain. And I might be remembering the wrong problem here, so we'll come back and look at this later on. But if we want to find the equilibria, it's not as bad as it looks. It just looks bad. So what are we even trying to solve for finding the equilibria? I'm going to set this whole thing equal to what? Right, equal to 0, and then try to solve for which of these things? N, I, beta, or mu? There is one right answer. It's got to be I, right? We're asking what value can the number of infected people have so that the rate of change of the number of infected people is 0. We're looking for the equilibria. So we're trying to solve for I. So I should factor out an I. I'm left with beta times n minus I minus mu equal to 0. So I'm either going to get I equal to 0, which makes sense, right? If you have 0 infected people, you're probably going to not get more infected people. So it seems like that would be it probably even is a stable equilibrium, I'm guessing. And the other one is going to be setting this part equal to 0. So we have beta times n minus I minus mu equal to 0. We have beta times n minus I equal to mu. We have n minus I equal to mu divided by beta. And then we're going to add I and subtract that. So we're going to get n minus mu over beta equal to I. Those are our two equilibria. And I guess without knowing any numbers, it would be hard to construct the phase plot here. Because, well, let's think about this for a second. I is a number of people. I should probably not be negative. So it seems reasonable, although I'm going to add some numbers here in a second. It seems reasonable to assume that our phase plot looks something like, well, here's I equal to 0, or I hat equal to 0, or these little hats. And then over here is I hat equal to n minus mu over beta. Now, I know it's not super easy based on the way this is all written out, but if you multiply this whole thing out, what would be the highest power of I? Show me on your fingers. Not that many. Way less than that. This many. 2. If you multiply this out, you're going to get beta times I times negative I. And that's going to be your negative beta I squared. And nowhere else do we get any higher powers of I. Right? You get beta times I times n and mu times I. So this is a quadratic in the variable I, and it's a downward opening parabola because your highest power is your term is negative beta I squared. Beta is positive, which I guess I didn't say, but it should be positive. So this is a downward opening parabola. So it looks like this, which means 0 is actually unstable. Okay, I made a bad guess. That's fine. It's okay to guess wrong. So I hat equal to 0 is unstable, and I hat equal to n minus mu over beta is stable. How do we know? Because of the little arrows, right? This is your di dt. Here your arrows go left, here your arrows go right, here your arrows go left. So that one's got to be the stable one because you're pointing towards it. That one's the unstable one. Now, what I left off from this problem, because I wanted to do it more generically, is they actually give you values for everything. They give you a value for beta, it's 0.08 in this particular version of the problem, a value for n, which is 800, and a value for mu, which is 33. So if you actually plugged in those values, you would see that your actual I hat here is 800 minus 33 divided by 0.08. And that still is positive because 33 divided by 0.08 is, I don't know, something in the range of 400-ish. Certainly positive. So you still have the same kind of graph here. All right, that's all for today. Try to stay dry out there. Welcome to Fallen Davis. If you haven't been here before, this is what Fallen Davis is like.
Thank you.
Oh, and yeah, and the thing went right. Yeah. If you wouldn't mind hitting the lights, I would appreciate it. Thank you. Oh, so much better. Mine's run. Thank you. Again, I will not be in office hours right now, but today's the last day of not having office hours, and then I will be back in my regularly scheduled office hours unless I say otherwise. You're welcome.
Fine.
Oh, sure. Yeah. That's all right.